Good afternoon, everyone. I'm Mimi Zhan from the Hong Kong University of Science and Technology. Today, I'm so glad to be here and give the presentation on the ultra-sensitive cement sensor with in-situ green carbon nanotubes. Here I would like to introduce our ultra-sensitive cement sensors from the following aspects, which are background, our strategy, experimental results, and the conclusions. Nowadays, the structural health monitoring has been widely used in the civil engineering structures to real-time monitor the condition of structures and help to keep structures in good service. However, the big problem for the current SHM system is that the commonly used sensors possess several disadvantages. For example, compared with structures, the durability and the strength of the sensors are much lower, which will affect the sensing capacity of the structure of the SHM systems in the long term. And the commonly used structures are generally incompatible with the structures, and this will decrease the properties of the structures when the structures are embedded in the structures. And besides, the high cost of the sensors also limit the large-scale monitoring of the current SHM systems. Developing cement sensor seems to be a feasible way to solve the above problems because the cement sensor has the advantages such as high durability, high strength, good compatibility with structures, as well as low cost. This is a schematic diagram of the cement sensor. In the fabrication of cement sensor, conductive fillers are generally added in, and they can form a conductive network in the cement sensor. When cement sensor deforms under external force, the distance between conductive filler also changes, which will enable the change of the resistance of the composites. With the external force, this will enable the composites to exhibit self-sensing ability. For this type of cement sensor, the sensitivity is usually evaluated by gauge factor. Gauge factor is a very important parameter for the cement sensor because generally the higher the gauge factor, the smaller the strain or cracks that the sensor can measure. We can see this from this table. For the metal field strain gauge, gauge factor ranges from 2 to 6. And with this gauge factor value, the smallest strain that the metal field strain gauge can sense is 0.1 microepsilon after amplification. And for the semiconductor strain gauge, gauge factor ranges 50 to 200, about 2 orders of magnitude higher than that of metal field strain gauge. Therefore, the smallest strain that the semiconductor strain gauge can measure is 0.001 microepsilon after the amplification. Therefore, in order to measure the strain or cracks at the micro level, we have to develop cement sensor with an ultra-high gauge factor. It is believed that a cement sensor with carbon nanotubes has the potential to get an ultra-high gauge factor. And as it is reported that the gauge factor of cement sensor with carbon nanotubes ranges from 54 to 704 in the literature, and this wide range is caused by the agglomeration of carbon nanotubes. As we know, the agglomeration is a big issue for the carbon nanotubes composite, and it significantly hinders the increase of the gauge factor of this type of cement sensor. And therefore, the key to fabricate cement sensors with ultra-high gate factor is to uniformly disperse carbon nanotubes in matrix. Our strategy to fabricate cement sensor with an ultra-high gate factor by carbon nanotubes is shown in this schematic diagram. In our strategy, firstly, we try to solve the dispersion problem of carbon nanotubes by in-situ synthesized carbon nanotubes on the surface of flash particles. And in this step, we optimize the synthesis condition to increase the content of carbon nanotubes so as to increase the dispersion efficiency. And then we incorporated these CNT and FA particles in cement mortar with a good dispersion of flash particles. The carbon nanotubes can also be well dispersed in the matrix so that we can get the composites with uniformly dispersed carbon nanotubes. And then we detect the piezoresistivity of these cement composites under compressive loading. After the synthesis process, we used SEM and TEM techniques to characterize the CNT and FA particles, and the commercial carbon nanotubes were also characterized for the comparison. And the result is shown in this figure. Figure A and Figure B are the SEM and TEM images of synthesized CNT and FA particles. And Figure C, Figure D showed the morphology of commercial carbon nanotubes. From Figure A and Figure B, we can see that carbon nanotubes has been successfully synthesized on the surface of flash particles. And compared with commercial carbon nanotubes, synthesized carbon nanotubes seems to be more fluffy. And then we detected these two types of carbon nanotubes, the dispersion of these two types of carbon nanotubes in water by optical microscopy. And the dispersion results are shown in these two figures. The right figure shows the dispersion result of the commercial carbon nanotubes. From this figure, we can see that after the ultrasonication, commercial carbon nanotubes tends to agglomerate together, and several big agglomerates can be observed in the suspension. This result suggests that the commercial carbon nanotubes are very difficult to well dispersed in water only by ultrasonication. And for the CNT and FA particles, the dispersion result is shown in the right figure. From this figure, we can see that no obvious agglomerates can be seen, and only dozens of black small stains that were uniformly dispersed in the suspension. This result confirmed that the synthesized CNT and FA particles had a better dispersion state compared with commercial carbon nanotubes, and suggesting that CNT and FA had a better dispersibility in water. Then we detected the piezoresistivity of the cement mortars and the fractional change in electrical resistivity of plain mortar, commercial carbon nanotubes cement mortar, as well as the CNT and FA mortar with increasing strain is shown in this figure. From this figure, we can see that for commercial carbon nanotubes cement mortar, plain mortar, the resistivities decreased slightly and linearly with increasing strain. However, for CNT and FA cement mortar, the resistivity decreased significantly with increasing strain. Therefore, CNT and FA cement mortar seems to exhibit a more sensitive piezoresistivity compared with commercial carbon nanotube cement mortar. From the background, we know that for the sensitivity of cement sensor, the it is usually evaluated by the gauge factor, and the gauge factor can be obtained by the slope of the linear fitting of FCR versus strain curves. After the linear fitting, the obtained gauge factors of these three types of cement mortars is shown in the right table. From this table, we can see that among these three types of cement mortars, the gauge factor of cement mortar made with CNT and FA particles was highest, and its gauge factor is even 50 times higher than that of cement mortar made with the commercial carbon nanotubes. And it is believed that the good dispersion of in-situ carbon nanotubes is the main reason for the ultra-high gauge factor of CNT and FA cement mortar. And then we investigate the gauge factor, the change of gauge factor with different CNT contents. And the result is shown in the left figure. From this figure, we can see that with the same addition of carbon nanotubes, CNT and FA cement mortar always exhibited a much higher gauge factor than that of commercial carbon nanotubes cement mortar. And the gauge factor of CNT and FA cement mortar increased with the increasing content of carbon nanotubes, and it reached to the maximum value of about 6,000 and at 2% of addition. And then in order to investigate the piezoresistivity of CNT and FA cement mortar under cyclic loading, we detected the FCR of this type of cement composite under cyclic loading, and the result is shown in the right figure. From the right figure, we can see that for the CNT and FA cement mortar, the resistive at 2% of CNT addition, the resistivity decreased with an increasing compressive load upon loading and increased to the initial values upon loading, suggesting that CNT and FA cement mortar exhibit a reversible piezoresistivity under cyclic loading. And during the loading, the maximum value of the fractional change in electrical resistivity reached to 70%, and this large resistivity change further confirmed that the ultra-sensitive piezoresistive behavior of CNT and FA cement composite. And this phenomenon lasted up to 40 cycles with high signal-to-noise ratio. This phenomenon suggests that this type of cement sensor also exhibits a very stable piezoresistive behavior under cyclic loading. Then, in order to further evaluate the sensitivity of the cement sensor in our study, we compared its gauge factor with other cement sensors from literature, and the results is shown in this table. From this table, we can see that for the CNT and FA cement sensor, the gauge factor is the highest among the different gauge factor values. And it is even 10 times higher than the highest gauge factor that currently reported in the literature, further suggesting that the CNT and FA particles has the great ability to fabricate cement sensor with an ultra-high gauge factor. According to the above experimental results, we can get to the following conclusions. Firstly, SEM and TM showed that carbon nanotubes were successfully synthesized on the surface of flash particles, and the dispersion measurement confirmed that the in-situ carbon nanotubes had a good dispersion state in water compared with commercial carbon nanotubes. And lastly, piezoresistivity measurement showed that in-situ growing carbon nanotubes were able to fabricate ultra-sensitive cement sensor with a gauge factor as high as 6,500. And the piezoresistivity of this type of cement sensor exhibit great stability, repeatability, and high signal-to-noise ratio, indicating the great potential application of CNT and FA particles, CNT and FA cement mortar in SHM system. And finally, thank you for your patient listening.
All right, thank you, Dr. Zhan.